Okay, so let's continue the global picture on approximate verification. So yesterday we talked about interactive proofs, and we essentially gave an example for graph non-isomorphism and for the permanent. Okay, now this is a co-NP problem, and this is a p to the sharp p problem. Okay. So now we switch to this second model, and then we will come to the third. Okay, the third is the one where you really find practical applications. Okay, not to say that two first are not interesting, but the two first are interesting for theoretical reasons. This is, of course, you have theoretical reasons too, but you also have real practical application. Essentially, here you are going to get into the area of computing without reading data, and this is a tendency that goes in computer science today, where you have too many data, so you can't really read the data, right? So, but you can do a lot of other things, and somehow you define a different computation model. And actually the theoretical picture is relatively open here. Okay, so you remember the definition? We defined, so the main definition yesterday we saw is that you have a language L is in the class PCP Rn Qn if there is a polynomial time verifier such that, so if the data is in a language, then there exists a proof pi such that v of x rho pi accept, and technically I should put here probability over rho that I accept is 1, and then if x is not in the language, then for all pi primes, then the probability that v accept on pi prime is smaller than 1/2. Okay, so that's the definition, and you see that it essentially takes the same pattern as the IP definition. The only difference is that the prover is fixed. It fixes a pi, and it can't change anymore. Now, what's important to realize is that okay, so if you remember, you access pi via you have to generate position I. Okay. Now, there are two cases. Either this pi is of polynomial size in terms of the input. So here, typically, the length of x is n. Okay, and there are two cases. So either are we talking about the polynomial in n size pi, or are we talking about maybe an exponential size pi? Okay, so it's important because it's going to condition the Rn. Imagine you have an exponential size 2 to the imagine the length of pi is 2 to the n. Okay? Now, how many? So, what is the constraint on R? The R cannot be, for example, log n. See, if the length is 2 to the n, and potentially you want to suppose that you can address any position, then Rn is going to be n. Okay, because you need n random bits. With n random bits, you have a position between 0 and 2 to the n, right? So, in other words, if I put maybe n to the cube here, then I can access, you know, something which is of size 2 to the n to the cube. Okay, and if Rn is log n, then in that case pi is of polynomial size. Okay, in this case it will be k log n. Okay, so if you have k log n bits, right, then you can address n to the k, something of size n to the k. All right, so that's why in PCP there are two versions. The version where Rn is log n, in which case you're talking about the standard pi, which is of polynomial size. But then you have a case where Rn is, for example, n cube. Okay, and here we're talking about exponential size proofs. Okay, so this is only interesting for, you know, theoretical purposes, but nevertheless, it's not quite obvious that, you know, if you want to concentrate, let's concentrate on these two classes. So O of, let's say, n cube. Well, maybe I should put here any polynomial. And then I want to concentrate on the fact that Q of n is always constant. Okay? And this is versus PCP of O of log n constant. Okay, so the real interesting cases is when Q of n is a constant, because constant means you can only sample. Okay, you cannot know the whole thing. You can only sample. So the question now is, how many random bits do you need? So indirectly, what is the size of pi? Okay, so let's take a very simple example where pi will be actually exponential, will be like this. But the advantage is that it will be simple to understand. To find a pi for the case PCP log n 1 is, you know, another game which is called a hard PCP, and we won't talk about it because it would be that would go into a totally different direction where I don't want to go. Okay, so let's talk about, you know, just imagine you have something you want to verify. You allow exponential size proofs, but you only want to sample the proofs. Okay? Is it feasible? Okay, so think about, first of all, you want to prove to somebody that some number n, well, okay, maybe I shouldn't write n, should write some big, so you're given a number, big N, okay, and you ask, is it prime? So it's a very classical story, okay, which was you know, a key theoretical problem until about 2000, because nobody knew if you could decide this in polynomial time without using randomness. Okay, so in 2004, somebody proved that indeed this is a polynomial time problem. But of course, the algorithm to decide primality is very complex, and in practice, nobody uses it. Everybody uses a randomized version. And for example, you may have heard about the Solovay-Strassen algorithm, which is the one used in practice. Okay, so when when I see people trying to break RSA or whatever, usually they play with primality, and that's you know, every time they want to, you are given a number, they want to check if it's prime, that's what they use. Okay, so just let me remind you how it works, because that's very simple. So essentially n is prime if you're going to compute a certain function and you're going to compare it to a to the n minus 1 modulo n. So let me check if, right. So if you all know this test, it's a very famous thing. Okay, so here it's divided by 2. Okay, so this is called the Jacobi symbol, but remember, it's something that is easy to compute given a and n. And then the question, so a is smaller than n, actually smaller like this. Okay, this is very easy to compute. Okay, this is also easy to compute. And the question is this equal to that? Now, if you're prime number, then it is true that this is for all a, this, you have this. Okay? And if you are not a prime, if you are a composite number, okay, then for more than half of the a's, it is false. Okay? So in other words, you have a witness a with probability 1/2. Okay? So in other words, the probability, so if n is prime, that implies this, and if n, people say composite, then the probability that this is, that actually these two terms are different, is bigger than 1/2. Okay, so, and this is essentially what the Solovay-Strassen test does, is that it picks random a's, okay, because otherwise there would be too many, and then it checks this identity. If it finds an a such like this, it says composite, and if it's always equal, then it says it's probably a prime. Okay? It only says it's probably a prime because it doesn't want to try all the layers. Alright? So in that sense, it's a probabilistic algorithm. It was actually one of the first primality testing, and it is used in practice. Okay? So all the guys doing securities and or RSA or whatever, that's what they use. Okay, well, let me give you, so this is going to be indirectly, that gives you a PCP proof of primality, which will be of exponential size. Okay? So why? Well, just imagine, what are you going to put on the string? Okay? What you're going to put on the string is essentially, you're going to enumerate, imagine you enumerate all the a's between 2 and n over 2. Okay? And then for each a, you compute this. So in other words, let's call this stars of a, this equation. Okay? So essentially what you're going to put on the tape is the value of star of a, which is either true or false. Okay? True if it's like this, false if it's like that. Alright? So imagine you write all the a's, and of course you have an exponential number of a's, right? Everybody see this? So the number of a's will be half of n, but in terms of the length of n, it's still exponential in the length of n. Okay, so you enumerate all of these guys. Okay? And now, why does it give you a PCP proof? Because you're going to sample. Okay? For each sample, you check the value. Now you redo this test to make sure the value is correct. Okay? And if it's always true, then you say, fine, I'm convinced it's prime. And if you find the witness, then you say, you know, I'm convinced it is not a prime. So depending what you're trying to prove. If you're trying to tell me that it is a prime number, then you better make sure that I never encounter this. Okay? But you can see that by just sampling, okay, the proof, which is of exponential size, I convince myself that indeed the number is a prime or composite, exactly as the Solovay-Strassen test would do. Okay? So the interesting thing about this primality testing is that here you have a primality test, but you can immediately convert it into a PCP proof of exponential size. Okay? There's no mystery about this. So at least it's a simple example. Okay, so the second now example would be satisfiability. So SAT, which is more like a, you know, computer science type. So imagine you have a SAT instance. So I defined this yesterday, but we can do it again with a specific example that I'll reuse at some point. So maybe my example I should put. Okay, let's put the example here. So imagine I have this SAT. So I have first clause P1 or P2 or P3. C2 is P2 or P3 bar or P4. C3 is P1 or P2 or P4 bar, and C4 is P1 bar or P2 bar or P3 bar. Okay, I'll use this example further. Okay, so a SAT instance, you're given a set of clauses, here 4 clauses, and you want to know if there is an assignment that satisfies it. Okay? And maybe there is an assignment here that satisfies it. Yes, most likely you can guess that I can make P1 true, P2 true, 3 clauses are satisfied, but this is, and then I make P3 false, so I satisfy this. Okay? So obviously, so my assignment should be 1 for P1, 1 for P2, and 0 for P3. Oh, and then P4 is anything you want, 0 for you. Okay, so this is a good assignment. And so this is a proof of size n. Right? Now, if I make a mistake, imagine instead of giving you this, I put a 0 instead of the 1 here.
It also works.
It also works, okay. But, and what about if I change this guy? See, it could be that if by changing 1 bit, you know, the valuation doesn't satisfy anymore. All right? So if you sample, you know, a long valuation like this, and if there is an error, you don't have any chance to find it, at least in this model. All right? The question is, can you find an exponential size proof? So here I have a linear proof. Okay, now, can I find an exponential size proof? And I will give you now a proof of size 2 to the n cube. Okay? Such that if you sample, okay, if it's correct, you will say it's correct. And if there is a mistake, you will find it with extremely high probability, even if there is 1 error in valuation. Okay, obviously I'm going to transform the valuation, amplify it, and in a mysterious way, by amplifying, I will also amplify the mistakes. That's essentially what I will do. Okay, now it's a very classical example. It's very useful to know this, and it's not very difficult, so let's do it properly. Now it is called, it has several names. It is called usually an Adamar code. So now, so essentially we're going to the valuation over there is going to be coded in a special way, which is called an Adamar code. So maybe you've heard about this Adamar code. And what is it? Okay, let's call this vector A. Okay, and imagine you study a function, a linear function, which I would call A sub x, where you view x as x1, x2, x3, x4. Okay, and A of x is what you would call also AX. So it's a sum of the AI xi, modulo 2. So now I'm going to do, everything is modulo 2. Everybody see this? So you can always, given a vector, associate a linear function, which I call A sub x, which is the sum of the AI xi, okay, modulo 2. Okay, so now imagine that instead of looking at A, I look at the graph of this function. So what is the graph of this function? So I'm going to enumerate all the x's, and for each of the 2 to the n x's, I'll give the value of the function. Okay, so it's an enormous table. So here the table would so you know you would start with 0, 0, 0, 0, and then what's the value of the function here? Well, on this example, okay, 0, 0, 0. Actually, on any example, will give you 0. Okay, then you enumerate all the x's. So you have 2 to the n. Right? And then you have the value of the function here. Okay? You see what I mean? Okay, so an Adamar code is a code which is totally crazy from the computer science point of view, which codes a simple binary word of size n by an exponential object, which is actually the function it defines in this form. Okay? Seems completely crazy to do this, but you'll see that it's not so crazy in this context. Okay? And this is why the redundancy comes in. You see, by having this function, you have also tremendous redundancy in the table. Okay? And because you have tremendous redundancy, then some miracle will occur. Everybody see this? All right. So now, if you're familiar with this kind of situation, just imagine it helps to think of the following problem. Let's suppose you take a different vector, different valuation. Let's call it b. So it defines a different function, b sub x, right? Imagine a and b differ on 1 bit, but in any case, it doesn't matter. What do you think the proportion of, in this table, so I have a big table for A and a big table for B's, right? If I take a random x, a random position here, what is the probability that the A of x equals B of x? 1/2. Okay, so here is something very important that, okay, this 1/2 is going to be this 1/2 here, right? So the probability that B of x is equal of A of x over x, taking uniform x's, is 1/2. It's not totally obvious, but you see, if you change 1 bit, okay, then indeed depending if it was 0, 1, you know, sometimes you're going to change the value, sometimes you're not, you know, but the other way to see it maybe is to imagine that
half of time you will multiply this change of speed by 0, and half of time you will multiply it by 1.
By 1, exactly, exactly. That's okay. So I'm going to use this a lot later on. Okay. So in other words, why will I use it? Because to check out, if you give me a evaluation like this, you know, first of all, I will have to check that it is a linear function. Okay. Now, linear function we talked about yesterday. Okay. So, given that table, I will apply the linear test that we saw yesterday. Okay. Then I will apply some other test. Okay. And I will convince myself with very few samples that what you give me is consistent with given valuation like this. All right. So if you're trying to cheat by putting you know, random values here, then you know, you're going to be caught. Okay, that's the idea. All right. So now, how do we build on this? Well, so imagine we do the following thing. So maybe I can erase this now. Okay, so the first step is to do something which is relatively standard, is to arithmetize, to replace these formulas by polynomials. Okay? And it's very standard because we'll be in a better situation once we have polynomials. So how do I do this? So it's for arithmetization. But you have to do it you have to be slightly careful. So obviously, when I see pi, I will consider that I have a variable p sub I. When I see pi bar, what should be the arithmetization of pi bar? 1 minus pi. Okay, so remember, we're going to interpret all the variables on 0, 1. Okay, so you have to think about this. So now, suppose I have an end. So suppose I have a phi 1 and phi 2. Okay. Then, so let's process. I'll call it a sub phi. A sub phi is a polynomial. Okay, so here's the transformation for pi, here is for pi bar, so now I have to transform a of phi 1 and phi 2, and you know, it's easy to see that you should try first a sub phi 1 multiplied by a sub phi 2. Okay, so you're going to process inductively, and now how do you arithmetize phi 1 or phi 2? Okay, so obviously, once you have seen it, you say, well, I'm going to do a phi 1 plus a phi 2, and you should not. For some reason, you should write here a phi 1 plus a phi 2 plus a phi 1 times a phi 2. Okay, there is a trick here. Okay, I can explain more later why you have this term. All right, okay. So now, so the first thing to see is the following. So if I have evaluation, So A. So this notation means this valuation satisfy the formula phi. Okay. Then you should see that if and only if A sub phi, A phi, so when you apply A on it, it should give 1. Okay, so for example, let's take a very simple example. Well, let's say P1. Imagine phi is P1. Okay, so when does, well, you replace the value, the first component of A, and you see if it's 1, and it says precisely when does A satisfy phi. So okay, this is sort of a trivial example, but believe me, the arithmetization is done so that it works. And now let's suppose we have this instance. Okay, so once I have this instance, then I'm going to do a small transformation in the following sense. Is that I'm going to say that so I'm going to build a vector. Okay, so let's imagine that C is a union of these clauses. So what should be AC of A? Well, it's going to be the vector, which is not the arithmetization of C1, but the arithmetization of the complement of C1. Okay, and then here the complement of C4 of A. Okay, so in other words, it's often the case when you have a SAT instance, instead of looking at the formulas, you want to look at the complement. Okay, because essentially you want to make sure that the complement of the formula is false. Okay, each complement of the formula is false, and by looking at the complement of a clause, we kill the or and replace it by an and the and is easier to handle because the or is kind of more difficult. Okay, you see that? Now, obviously, if A satisfies the end of the clauses, it's the same thing as saying that AC of A is going to be the vector 0, 0, 0, 0. Okay, because the formulas have to, the inverse of the formulas, negation of the formulas have to be false, so therefore they are zeros. Okay, and that amounts to saying that they're all satisfiable. Okay, so let's do this example so we see better. I guess I can erase this now. So I have 4 polynomials and I'm going to play with this. So the first polynomial, A of not C1 is what? Okay, so remember you take the negation, so now you have P1 bar and P2 bar and P3 bar. So P1 bar is 1 minus P1 and you multiply. Okay, so it's going to be 1 minus P1 times 1 minus P2 times 1 minus P3. Okay, I'll have to develop this later. Let's do the same thing for C2. And it's going to be, so P2 bar 1 minus P2. Then P3 times P3 times 1 minus P4. Okay? All right, so let's make some room here. So I think I can erase this because Okay, so A of not C3 is 1 minus P1, 1 minus P2 times P4. Okay, so you correct me if I make a mistake. So now it's going to be P1, P2, P3. Okay? All right, so now this I have to arrange a little bit, and it's going to be 1 minus P1 plus P2 plus P3 minus plus the pairs, so P1 P2 plus P1 P3 plus P2 P3 minus P1 P2 P3. Okay, then C2 is going to be P3. So everything you have to think of it a constant plus a polynomial of degree 1 plus a polynomial of degree 2 plus a polynomial of degree 3. Okay? Now it has to follow this shape, but I want to, for some reason you'll understand in a minute, I want to write it in detail. So P3 is a constant, thing, and now minus P2 P3 plus P2 P3 P4. Okay, I think I get only these two terms of degree 2, and then plus P2 P3 P4, P2 P3 P4. Okay, now check. I make mistakes possible. So okay, now the third one is P4. So now the constant is 0. P4 minus P1 P4 plus P2 P4 plus P1 P2 P4. Okay, and the last one is P1 P2 P3. Okay, here are my 4 polynomials. All right. So remember, if I give an A, if I evaluate on some A's, then the A satisfy my clauses if and only if I get zeros here. Right? Clear? All right. But the key thing is going to be the following lemma. Let's suppose now you take this vector and you multiply by some random vectors. Okay, so you're going to look at AC A times R for some random R. Okay, this is a vector, this is a vertical vector, random. Okay, so this is a value, and it's 0, 1. Okay? So for example, let's suppose R is 1, 1, 0, 1. Okay? So if R is 1, 1, 0, 1, it means that I will take this, I'll take the first polynomial, I'll take the second polynomial, and I don't take the third because I get zeros, right? and then I take the fourth. So I take first, second, fourth, and I evaluate on A. Okay? All right. So let's compute this. And you see, because it simplifies. So this simplifies with this. And somehow the P3 simplify here. Right? So now I write this as 1 minus P1 plus P2. Okay? And then the second plus a certain number. Okay, so now what do I get in P1, P2, P2, P3? That simplifies. So I get P1, P2 plus P1, P3 plus P3, P4. Hope I don't make a mistake. And then I end up last term P2, P3, P4. Okay? All right. And then I have to evaluate this on A to get the result, right? All right. So of course, if I evaluate on A, then I get A1 minus A1 plus A2 plus, well, same thing with A's, plus same thing with, you know, replace the P by the A's. Okay. But then I want to write, you want to think of A1 plus A2, actually, you know, if you think of the Hadamard code of A's, okay, because you have to think of A as a function. So A1 plus A2 is essentially the function A. Well, let's call it that is multiplied by some vector. So the vector will be here 1, 1, 0, 0. Okay. So at this point, I take it back. I don't look yet at the function A as the Hadamard code. I just look A1 plus A2. You can always write it as the vector A1, A2, A3 multiplied by 1, 1, 0, 0. Okay? So you can also write this polynomial of degree 2 as something like A times A, which is, see, these are all pairs, AI, AJ, multiplied by some other vectors. Okay, so for example, the first component here is a pair A1, A1. I don't have A1, A1, but I have A1, A2. So the first component will be 0, second will be 1, and then I will have 16 possibilities, 4 by 4. And then I have the third one is also an A times, okay, A times another vector. Okay, this time this guy has 4 by 4 by 4 dimension, and there is one value which is 1 somewhere, all the other are zeros. I don't know where. Okay? So you want to write this as a certain vector. So you want to write this expression as, there is a 1 here. So you want to write it as B0 minus A times B1, or plus A times B1, or minus, keep the sign here, plus A times B2, plus A times B3. Okay, for B0 is a value, it's actually 1. B1 is this vector. B2 is some other vectors of size 16. B3 is another vector of size 64. Okay, is that clear? Now, what have I done? I picked an R, random. So where was my R? Here is my R. Okay. If I take another R, I will get a different B's. Okay. The B's I get here, they're totally dependent on R. Okay. And now I should evaluate this, and the question is, do I get 0 or not? Okay. So in other words, if this is 0, 0, 0, 0, okay, if I take a random R, I should get 0. Okay. All right. But you see, the whole thing is what you're doing here is you're testing. So to make sure that you can evaluate A on B1. So this A B1 here, it will be exactly the same thing as writing it's a function A applied to B1. Okay, so here this is where we're using the Adama code. I rewrite A B1 as the function A where you apply on B1. Okay, so if you think of A as a big table, all right, so essentially I'm looking at the value on that table for the vector B1. Okay, that's exactly what I'm doing. Okay, and then I can do the same thing for AA. So AA, so it's a function which is, so now it's a linear function on 2 arguments. So it's a table of size 2 to the n squared. Okay, and you evaluate it on B2. And the last thing is the function A. Now this is a table of size 2 to the n cubed, and you evaluate it on B3. Okay? Okay, so now what is my pi? What is my proof? Okay, so my proof is essentially the proof pi is the Adama code, so let's see, the table for the function A sub x, the table for the function is A sub y, and the table for A on z. Okay, x is a vector of dimension 4, y of dimension 16, z of dimension 64. Okay, so somebody now who wants to convince me that the clauses are satisfiable is not going to give me this. Okay, he's going to give me for this A this table, this table, this table. So you know this is an exponential size thing, right? All right, and now how do I proceed? Now I can only sample this to make sure I'm convinced. How do I sample? I take a random R, like this guy. From this random R, I do exactly what I've done, and I get the vectors B0, B1, B2, B3. These are the values I will give for X, Y, and Z. Then I get the result, and I check this. Is it true or was it false? Okay? So that's the key component of the test, so which is called, let's call it a satisfiability test. So satisfiability test is a random R, then computation of the vectors B0, B1, B2, B3. Okay, so that's why it's important to have 3 variables at the max, you know, for each classes. So that's why actually here we're doing 3 set and not set. Okay, should have been said here 3 set. Okay, so for random R I get these 4 values, and now I evaluate A on B1. So I take B0, B0 is a constant. I do plus A of B1 plus AA on B2 plus AAA on B3. Do I get 0 or not? If I don't get 0, I don't believe that this is a satisfying assignment, so I reject. Okay? If I get 0, should I believe that this is a satisfiable assignment? Not quite. Well, not quite, because I want also, for this to work, this table you give me must correspond to a linear function. Okay? You've seen that these are linear functions. So I'm going to do, to check, I will have a linearity test. Okay? Each table has to be a linear function, and we've seen the test for linearity yesterday. Okay, so I take random points, I add them, and make the image of the sum. Okay, and this is, I check if it's correct. And then the last test is a consistency test. The consistency test is going to make sure that AA is consistent with A, and AAA is consistent with A. Okay, because here you could give me a table that is totally unrelated. Okay, they're all linear, but they are, they're mixing. In case you do, this satisfiability test is not going to be quite correct. Okay, but if it's consistent, if the functions are linear, and if the satisfiability test works, then we're in business. Okay, and then being in business means the following thing. Okay, now I can erase this. So the fundamental result now is the following theorem. Okay, so if C is the end of the CI, is satisfiable, so it's, so if C is satisfiable, then there exists an A such that the probability that ACAR over R, the probability that the satisfiability test, so ACAR equals 0 is 1. And then if C is not satisfiable, well, then for all A, the probability, okay, that all the three tests are okay, but is less than 1/2. Okay. Actually, yes, I can say it like this. Okay, so in other words, if it's satisfiable, there is a proof. So there is a couple of tables, okay, such that you pass the test, all the tests are okay, so, with probability 1, everything is fine. And then if it's not satisfiable, then I don't pass the satisfiability test, provided I pass the others with no more than probability 1/2. Okay, and this, of course, the key to this is to figure out that if there is the slightest mistake in the tables, okay, then you're going to use the remark that we've seen before, is that the probability that you get a matching answer, okay, in case there is a mistake, against the random R is 1/2. Okay? So therefore, with probability 1/2, something, if you get something wrong here, okay, the test will catch it with probability around 1/2. Okay, so you won't convince the tester to accept with more probability more than 1/2, which is essentially what we're saying. Okay, so I don't know if you realize what we have done here. We've done something which is totally unnatural. We replace a witness which is linear, okay, by a witness which is exponential, okay, but it has this magic property that you can only sample it, and if there is an error, you will find it. Okay? And of course, this is not the case for this. If there is an error here, you will not find it with probability, with high probability. Okay? Actually, you will not find it with probability. I mean, the probability that you find it is 1/n. 1/n is like 0. Okay? So this is what we call the easy PCP. Why is it the easy PCP? Well, because what we have done is something simple. Okay, it's simple in the sense that we arithmetize and we use the property of linear functions. Okay, to figure out, you know, that we match the PCP conditions. But the drawback is that we have an object which is of exponential size. Okay?
So the whole point was not to read this linear witness, but to sample kind of fixed number of bits,
yeah,
and make sure that it's satisfied.
Yes.
But at the same time, we need to make read the input fully, kind of make this.
We don't read the input fully. We have an exponential size input, but we only
I mean the three-type problem.
Yes.
Yeah, we need to at least make these computations.
Oh, yeah.
So we make computations and then
let's see.
Some finite number of bits, and that's it.
Yeah, of course we see. In terms of the input, we do read the input. Here, we're not cheating yet. We're not sampling the input yet. That's what we're going to do in a minute. Okay, so the input we read. Okay, the question is, what do we do with the witness? Do we read it or do we sample it? We sample the witness.
But with input, we actually also sample it, because it depends on the random vector R. We can read only parts of the clauses.
Yes, but in the worst case, you may read all of them. Yeah, sure. Now you read all of them. Okay? You have to find the vectors B0, B1, B2, B3 for each R.
Since you run the test several times, you're very likely to read all clauses.
Yes, somehow. Okay, so now, of course, so the question was, well, could this work with a polynomial size proof? Okay, and of course the answer is yes. But the answer is yes, and it is a hard PCP, but it introduces a lot of techniques, okay, mainly based on expanders. So maybe you've seen this concept somewhere. So this is okay. So if you have a small proof, polynomial size proof, what you need to do is to essentially amplify the errors. If there is one error, yeah, you must apply a treatment so that you put the errors everywhere. So it's called error amplification, and you can do it with a polynomial time object. And this is even more magic than this. I mean, for some people it's magic, for some people it's not. What you'll see after is real magic, because we will switch to the area of just sampling the data, the input. Okay, here we do read the input, we just sample the proof. Okay, so that's pretty much all I want to do for this PCP. I give you one very simple example, another one which is considered simple. So that gives you a PCP. So technically, that gives you a PCP n cube 1 protocol to check 3 satisfiability. Okay, that's the way it's usually phrased. But I don't go into the PCP log n because I want to switch to property testing. And now, if you remember the linearity test, so the linearity test is you're given a function, you want to figure out is it a linear function or not. Well, it is some kind of property testing, okay? Because here you have this table and you sample the table. So you sample the data is a table, okay? And then you decide if the function is linear or if it is far from being linear using the distance I introduced yesterday, which is a natural distance on functions, essentially, you know, the proportion of input on which 2 functions differ. And then, of course, if the function you're given is almost linear, so you're saying if everything is fine except 1 point, for example, okay? By sampling it, you will not find it, of course. But the magic is that you can correct it. In other words, if by chance somebody asks you for the value of the function, you don't rely on applying the table. You apply the table and apply on some random values, and you do some interpolation as we did in the second example, and you take a majority answer, and this is your answer. And this answer will be correct. Okay? So you have a wrong function, and you correct it provided it is close to being linear. Okay? It's not something you can do if you're far from being linear. All right? So now we're going to play with this key notion and apply it to real concrete problems. Okay? All right. So remember, the first ingredient is the distance. Okay? So now property testing starts, everything is like what we've been doing so far, but now we have a distance on the object. Okay, so historically, property testing was, well, actually, the linear test was one of the first examples, but then people moved into real finite structures that people like in computer science, and then the first example was graphs. Okay, and we've seen the edit distance. Edit distance. Okay. Okay, so you edit the graph. Okay, and now people figure out some properties that are, of course, when you play this game, you want to look eventually at hard properties, and then you want to see, okay, can I decide hard properties by just sampling the data? Okay, which seems counterintuitive. Okay, so the first example of this was 3-colorability, which is an NP-complete property. Okay, you know all what 3-colorability is, so given a graph, you have to decide if you can color it with 3 colors. So you assigned colors to nodes, and you want nodes connected by edges to have different colors. Okay? So of course, the more edges you have, the more difficult it will be. And if you have a complete graph, it's impossible, of course. Okay, because you have too many edges, and then you have conflict. Okay, so given a graph, it's very hard to decide if it's 3-colorable. There is no polynomial time algorithm that we know that does it. But there is a constant time algorithm that approximate. Okay, this is the key. Okay, so now, what is going to be the condition? So the key definition is going to be what we call an epsilon tester. So there is now an epsilon. Okay, remember? Okay. So what is an epsilon tester? Okay, so it's a randomized algorithm. But you can think of a verifier still using random bits, such that okay, so let's say for language L. Okay, so it's a randomized algorithm, and in a minute I will say that the number of queries is constant, doesn't depend on n, the size of the input. Okay, such that, okay, so if x is in L, if we follow the same type of definition, then the algorithm, let's call it A on x should accept. Okay, and I write it like this, and technically there should be probability that A accept is 1. And the probabilities are on the random choices that the algorithm makes. Okay, so the algorithm flip coins. So what is a probability space is a set of essentially binary sequences. And now there is no error if x is in L. But then if x is epsilon far from L, then what do you expect? You expect the algorithm to be correct with high probabilities. Okay? So probability on row that AX is, say, so incorrect is smaller than 1/2. You could write it like this. But usually people don't write it like this. Usually they would say, they replace this by probability that AX reject, which I write like this, is big. And big, you may see, for example, 2/3. Or you may see 1 minus epsilon. Or you may see, well, okay, we have different options here, but they're all equivalent. Okay? This is, so when people say, so I reject with high probability, you know, depending, maybe it's easier to understand, you know, I reject with probability, well, should be epsilon here, 1 minus delta. Okay, it's not the same epsilon, no? Well, but think of delta 10 to the minus 10. Okay?
Why it is not enough to reject with some positive probability?
It is enough.
Say, you just reject this probability delta, which is greater than 0.
That would be okay too. But the reason we don't write it like this, I'll tell you what, because of course people make variations where they don't put 1 here. So then they put, say, 2/3, and out of symmetry they put 2/3 here. Okay? But if you go for 1 here, then you can put any fixed probability there. And actually, if you want to play this game, you can also play 1/poly probabilities. Okay? What you cannot put is 1/2 to the n. Okay? But 1/poly, 1/n, for example, is fine. Okay? All right. Okay, I stick to you know, maybe 2/3 or whatever, but that's enough. All right. So now the key. Okay, now the key thing here is. Okay, so I forget one notion here is, so the query, so the Q sub n is O of 1. Okay, Q sub n, remember, is like in PCP, the number of queries. Okay, the number of times I'm going to query my data. Okay, then you have to define what is a query. All right, so on graphs, and that creates, some peculiarities. There are two cases. You have the case of dense graph. So dense graph, think of graphs with many edges. Technically, you have the number of edges is bigger than, say, a fraction of the number of, so you have order of n square edges, okay? And sparse graph number of edges is less than, say, beta sum n. Okay, it's a. You may find other definition of sparse graphs. It's kind of thing, but dense graph, everybody agrees. You have many edges. Okay, so if you have many edges, what is a query? The query is you take random nodes. Okay, so you take certain random nodes. Okay, so if you have a k queries, for example, k query, then you have, for example, 4 points here. Then you take the edges, so you take the subgraph spanned by the given entrance. Okay, so here the given entrance x is a graph. So a graph for us is a domain and a set of edges. Okay, so if you take random points, say v1, v2, v3, v4, then you put edges if there is an edge in E. Okay, that's what we call an induced subgraph usually. That's what you're going to see. But you see, now if you have a sparse graph and you do the same thing, what are you going to read? What is likely to happen if you have very few edges? Beta sub n edges, beta n edges. A be empty. Okay, so you take k nodes and the graph is empty. So you're not going to go very far with that. So you need another model of queries. Okay, so for dense graph, you take induced subgraphs. That's what we're going to do in a minute. Okay, for sparse graph, it can't be the same. And for sparse graph, what you do is you take V1 and you take its neighborhood at distance k. So you take all the, all the nodes that you see within distance k. Okay, but then you do it for V1, you do it for V2. So in other words, you get neighborhood like this. Okay, they may connect, but most likely they won't. Okay, so you get k neighborhoods. This is what a query is in the case of sparse graphs. Okay, totally different model. All right.
One query is how much edges, vertices?
In this model, you can't predict. So.
I mean, so I take V1, V2, V3, V4. How much can I take?
No, the random point is the VI. But given a random point, I look at this neighborhood at distance k.
Okay, and k is?
K is the number of, is some fixed parameter.
Okay.
Okay, sorry. So
one query is one vertex with this neighborhood.
For?
One query in this case is one vertex and its neighborhood.
Yes. Typically, so this works very well when you have, say, graphs of bounded degrees. Imagine that the degree is bounded, so therefore the neighborhood here as distance k is also bounded by d to the k. So you have bounded neighborhoods, okay? Therefore you have a finite object. If the degree is not bounded, you may get a point which has a very large neighborhood, and you could eventually get the whole graph, which you want to avoid, because if you get the whole graph, essentially you sample, read the whole data, so you don't want this. Okay? So think more like dense graphs. Okay? And for 3 colorability, dense graph is an important case, because if the graph is sparse, most likely it's 3 colorable. Okay? So the interesting case is the graph 3 colorable when it is dense? So therefore I take the previous model where I take k points and the induced subgraph. Okay? And so the first observation. So this was, of course, one of the founding papers by, a couple of authors, but Goldreich did about maybe 97 or something, 95. There are several authors, right? But this was one of the founding papers on dense graphs property testing. And of course they take, an NP property. So it is hard. Question, is it testable? All right, so I define what an epsilon tester is. And actually I forgot, the condition I said that the number of queries is constant, okay? So the Q sub n is O of 1. Okay? That's important. Now, I didn't say what is a testable property. So a property is testable if there exists an epsilon tester that satisfies all this for any epsilon. Okay? Because it could be that for epsilon equals 0, 1, it works, but if epsilon is 0, 0, 0, 0, 1, it won't work. There will be a threshold on the epsilon. Now, if it works for any epsilon, then the property is testable. K is going to be a function of epsilon. Typically, it's going to be 1 over epsilon. Okay? So, a property is testable there is, or if there is an epsilon tester that's a uniform for all epsilon. In other words, it's the same algorithm. Whatever epsilon, you don't change the algorithm, when epsilon changes. Okay? The complexity of the number of queries is going to depend on epsilon. Okay? But that's all. It doesn't depend on n. Okay? Okay, so now, the first example, and this example plays a role of so this example or this example here, because it's very simple. So what could you imagine as the simplest test for 3 colorability? Okay, so you take a sample, you see a subgraph of size 1 over epsilon. Okay, so you take a random subgraph of size 1 over epsilon. It could be that it is 1 over epsilon square. I have to remember exactly the numbers, but it's either 1 over epsilon or 1 over epsilon square. This is a random induced subgraph. Now, what do? Well, we check if it is 3 colorable. Okay? And it's a finite graph. So eventually we can do it exhaustively. Okay? And we repeat this test. Maybe a number of times, that depends on the epsilon. Okay? And the miracle is that if the graph is 3 colorable, take an induced subgraph, it will also be 3 colorable. Okay? Because you have less edges. Alright? And now, and this is a hard thing to prove, that if you're far from being 3 colorable, then the probability that you find a sample which is not itself 3 colorable is extremely high. Okay? Which is exactly what you would expect. For example, if you take the complete graph, okay, it's not 3 colorable, sample it, then you'll find complete induced subgraph, okay, and they won't be 3 colorable as soon as this is bigger than 4. Okay, but you know, this works for every.
What is epsilon phi in this case?
What is epsilon?
What is epsilon phi in terms of colorability?
Oh, epsilon phi from 3 colorability means the number of edges you need to remove to make the graph 3 colorable.
Oh, okay.
Okay,
Just in terms of removing edges.
Obviously, if you want to go to 3 colorable and you're not, you don't want to add edges, right? You want to remove edges.
I don't want to remove vertices.
Sure.
It's not for.
But remember, we work with the edit distance.
And so, in the edit distance, we are not allowed to remove vertices.
With the edge distance, typical edit distance, okay, in the classical edit distance, you don't remove nodes. But in some variations of the edit distance, you do remove nodes. And I don't think it makes a difference for this property. Yeah? But you're right, it's a very, very good question. Classical edit distance, if you remove edges, so you get isolated nodes, but you know, you don't worry about the isolated nodes, but they still exist. It's a key point. Okay, so I don't want to prove this. It's hard to, this result is hard. It's heavy combinatorics. I want to move to something which is somehow easier, and you will see that the arguments are not necessarily so easy. Okay, so I want now to give you examples where I work not on graphs, but on words. Okay, so you just imagine you have binary words, and for change, imagine my word is on the alphabet A, B, so I get A, B, B, A. Okay, that's my word. All right, now, maybe some of you know the edit distance on words. So edit distance on words, it's very standard. It's not ambiguous as in the case of the graphs, where you have to specify are we working on the same domain or so on and so forth. Here, essentially, for example, if I have 2 words, this, okay, this is W, this is W prime. What's the edit distance? So remember, edit distance on words, you can suppress letters, introduce letters, modify 1 letter, and you have to do it in a minimum way. So how many edit operation you do?
And we can see there's a distance without weights.
There is no weight here.
Weight 1 for all.
Yes, the cost is 1 for each edit. Okay, so
2 seconds.
what?
2.
2. Okay, so the absolute distance will be 2. I guess you remove this one and you replace this guy by A. Right? And you can usually see by looking that you can't get 1. For example, right? By exhaustive search. I mean, you apply all the 1 transformation and it doesn't work. So it's 2. And then if we're going to look at the distance relative. So we divide by the maximum length, which in this case it's 1, 2, 3, 4, 7. Okay, so the advantage of the edit distance is that you can compare words that don't have the same length. Okay, because of course usually people compare this distance to Hamming distance. Okay, so the Hamming distance, the classical Hamming distance, assume that you have the same length. Okay, but if you don't have the same length, you can extend the Hamming distance by saying, look, you put anything. So you first make, by default I add A's until I get the same length, and then you can see that here the Hamming weight, so the Hamming is just a modification, so the Hamming would be still 2, and the relative Hamming would be 2/7. Okay? Now, obviously, you can think of words that are going to be with a small distance for edit, but big distance for Hamming. Okay, the Hamming and edit are not going to coincide. And so first of all, I claim that Hamming is always bigger than edit. Because, you know, if I can do it with Hamming, and always can do it with edit, you know, modification is the same operator. I have more operation here, so therefore I expect the distance to be smaller. Okay? Now, if you can see a case where the edit will be 1, say, and the Hamming will be n. Can you think of an example like this? And, okay, example like this exists. So think of this example. Okay, so say A, B, A, B, A, B versus B, A, B, A, B, A. Okay? Hamming distance is maximum. You have to change all the A's in B's, all the B's in A's. So distance is n. Okay? Now edit distance, you remove the first B, and you're almost there, and you add it there. So 2. Okay? 2 over n, so in this case the relativized is 2 over n. Well, 2 over n is like 0, because n is going to be large. Okay, obviously we're not going to look at the inputs of size 10 or so on. You know, we're looking at big data, so think of n as a billion. Okay, otherwise, no, it's useless. Everybody understand this? All right. Now, there is a third distance that I want to introduce, and it's called, I want to add an extra operator to my edit. So if you're in front of an editor, you know that, what do you do in front of an editor? Well, you type, sometimes you erase letters, but sometimes you do something funny. You select a paragraph, for example, and move it somewhere else. Okay? It's called a move. Okay, and in classical computation, it's called usually cut and paste, no? Cut and paste, which is a difference than copy and paste. Because copy and paste is that you select a paragraph and maybe you copy it in several places. I don't want to do that. Okay? But I want to do a cut and paste. So in other words, I want to take a chunk, move it somewhere else, and it takes one step. I count it as 1. Okay? So typically, for example, if you have the AA and the BBs, okay? And the other guy, let's suppose you have the BBs and the AAs. This is W, and this is W prime. Okay, so from the edit point of view, we're in bad shape. We have to change all the A's in the B's. Therefore, the edit is, relativized edit is 1, or absolute distance is n, and the distance with move is 1, so relativized distance is 1 over n, which is almost 0. Okay, so you have this EDM, so edit with move distance, which is smaller than edit. Okay? All right, so maybe we can make a pause, and then we have essentially everything. These are the 3 distances I'm going to play with. So Hamming, in my mind, I mean generalized Hamming. So you complete first the word so that you have equal length. Okay. I don't want infinite distances. Okay, distances are relativized between 0 and 1. Actually, if you only do this, the distance will be between 0 and 2. Okay, usually people take 1/2 of that. Okay, because think of AA and BBB. you need well, you need to erase everything and to write everything. So it means 2n divided by n, so it means 2. Okay, so if you only take the absolute distance divided by n, you end up with a value between 0 and 2. So that's why usually people take 1/2 of that to scale it into 0, 1. Okay, so think of, everything is scaled between 0 and 1. And when people talk about epsilon distance, so epsilon distance means epsilon is 10 to the minus 1, okay, and epsilon eventually goes to 0, okay, so that's the idea that you have here, okay. So then make a pause, and then I switch to the video projector because I want essentially to address two types of problem. Okay, so first, a very simple problem. You give me W and W prime, and I want to essentially decide if W is W prime. Okay, so I can't make anything simpler. Okay, so given W, W prime, I want to decide equality of two objects, but I don't look at the object. I just sample the object. Okay? Right? And then after that, I fixed any regular expression, and I want to decide if I am in the regular expression, so if I'm accepted by an automata. So this is a basic operation in computer science. But remember, I don't want my automata to read W. I don't know W. I only have samples of W. Okay? All right, so last thing before we stop is that now what is a query? So a query, well, it's going to be exactly like in the case of a sparse graph. So in the case of a sparse graph, a query is a random position, and then we're going to read some neighborhoods, and we'll read the subwords up to some k. And usually k is going to be 1 over epsilon. Okay, so that's a query. Okay, so you take a random position, you read k, and the question is it enough to decide this, to decide that, and to decide many other problems? And you can think of essentially, modern way of computing is exactly this. You forget the data. First of all, you have errors in the data. The data is not really totally, it's not perfect, so you don't trust it 100%. So why do you want to read it? If you read it, the result will be wrong with extremely high probability. What about sampling it and being right with high probability? Seems like a better approach. This is where I teach in Paris. Some of you know Paris. This is in the center of Paris. Okay, so this is essentially the resumes of what we're doing. These are 3 models, and now we are doing this, right? So here we were sampling the proofs. Now we want to sample the data. Forget about the proof. Just sample the data. Okay? All right, so this is where we are. Here, woods and trees. Okay, so now, so I want to look at the simplest, problem, equality of two strings. Okay, because already we're going to learn a whole bunch of things, and we're going to build on that. Okay, and it's the most natural thing. How could you, for example, think about Hamming distance. You remember? Well, the distances are they are behind. So we have Hamming, edit with moves. Okay. So I'm going to give you a tester for the edit with move distance. Okay. And now either a tester for the edit and a tester for the for the Hamming. I don't think so, but it becomes tricky. So we're going to see this in a minute. All right. All right. So here are the typical motivation people give, to study property testing is, you have noisy inputs, and sometimes you want to check things approximately, and so on and so forth. Okay. So that's. Okay, so this is essentially what I also talked about yesterday. I want to look at big databases. I have different sources where you can imagine that you have big words on each source. And now the game is, I want to combine these guys in a certain way. It's not fixed in advance. For example, I do this, but maybe I want to do this. Sometimes maybe I want to do reverse. I want to take this guy reverse, and so imagine. And for each of these combination, I want to have very quickly the answer to this, okay? And never read the data. So this is the goal. Okay. Now we'll see the Twitter business in a minute. All right. So this is the definition of a tester, an epsilon tester. So here the notation are a bit different because it's adapted to a general structure. Now think of, this is a word, but think of a finite structure of a class K. That's how you would define it. You have if the property is satisfied, you want to accept all the times. And if it's epsilon far from F, you want to reject with high probabilities. Okay. Good. So another picture which is useful, and in the classical satisfiability, if you have a property F here, so it divides the class of structures in two parts, right? The one that follow F and the one that satisfy not F. Okay? And now we have three parts. We have the one that satisfy F, the one that are epsilon far from F, and the one that are epsilon close. Okay, so essentially, if you think of the property, I want to make sure that if I'm here, if I'm there, there is no error. If I here in between, there could be some error. Okay, the blue line here is that you imagine that you're comparing two properties: the property defined by the black line, and another property is a G, defined by the blue line. Okay, and you see that these two properties are very close because every time you are not in one, you're actually close to the other. Okay, so it's something you want to check sometimes. Okay, it would be like given two regular expressions, tell me if they're close, in the sense that every time I have one word in one, the word will be close to the other. Okay, which is also very useful. Okay, so now this is a catch on the edit distance with moves. So remember, the distance of a word to a language is the minimum of a W prime in L of distance of W prime. Everything is cool with this. All right, now here's an example of a move. And what's also useful is to figure out similarly on trees. Okay, so what is an edit on trees? You imagine that you remove edges or add edges. Okay, you have to think of what is removing an edge on a tree. For example, if you have a tree like this. Okay, suppose you want to remove this edge. Well, figure out that the distance is going to 0. Okay, so eventually these two edges will become edges of this node. Okay? This is removing an edge. And adding an edge will be the opposite operation. Okay? Now what is a move? The move is you select a subtree and you stick it somewhere else. This is a tree. This is a move on trees. Okay? It's actually very, very useful. Okay. All right. So now here's our first statistic vectors. So we're going to now enter the world of statistics, relatively simple statistics. Okay, And so, okay, when you go into statistics of words, there are two important statistics. The block statistics, which I write as a B stat, and the uniform statistics, which I write as a U stat. And all of these look as density vectors. The sum of these values is equal to this value. Okay? So you can interpret this vector as a probability. Okay? And what it is a probability to observe a certain subwords of length k in your word if you select a random point with uniform probabilities. Okay? So another way of saying this is counting the number of occurrences of various subwords, starting with 0 zeros and ending with 1 1 1. Okay? So if you fix this length here, so this length is k, and in the future case you have to think of 1 over epsilon. Okay? So if you want a tester for an epsilon tester, then you fix k is 1 over epsilon, and you're going to build the statistics. So the block statistics does something differently. The block statistics look at blocks that are distinct. So the first block, second block, they alternate black and red. Okay, so 1, 2, 3, 4, 5, 6 blocks. Okay, that explains why I have a 6 here. And this is a vector for k equals 2. So I looked, okay, because I make blocks of size 2. So now I just count how many 0 zeros I have. Well, I have 1, which is here. How many 0, 1 I have none. How many 1, 0? I have this 1, 2, 3. It should be 3. Why is it 4?
Black one.
Huh?
Black one.
Ah, yes, thank you. Thank you. 1, 2, 3, 4. Okay, and then 1, which is 1, 1. And it is
Black one.
Yeah, the black one here. If I'm too close, I don't see. All right? Now, so this you take blocks as, separate blocks, right? In these statistics, you don't take blocks. You take a random position, and you have here 11 possibilities. Why 11? Because you have this possibility, but you don't have this one, because you don't see a word of size 2, but you have this one. Okay? So the number of position is n minus k plus 1. Okay? Okay, so it should say n minus k plus 1 shingles. That is a word used in English. Okay? And you can see now that you get slightly different statistics, because you have a 0, 0, but you have 4 0, 1. This one, this one, this one, and then maybe another one I don't see. Okay, we have 4. Okay? So the statistic is this. Is that clear? All right. So you have to think, of course, k 10, and this is going to be of size 2 to the 10. Okay? So 2 to the 10 is 1,000, you're still okay. But if it's 100, 2 to the 100, you're going to get into trouble. Okay? But we'll see this in a minute. So if you have a word of size 1 billion, and you want a vector with k equal 100, the dimension of the vector will be 2 to the 100, which is something crazy, but you will still have 1 billion values only in this vector that are non-zeros. All the others are zeros. So you'll get a very sparse vector. You see that? Okay. All right, so what's important here is you want to interpret, so in computer science, this is called a k-gram. Okay? And a k-gram, indirectly, it's something that Google does all the time. So when you want to classify documents, so for example, you have every day you have the Google robot come to your website, look at all accessible documents, it finds the documents, it reads it, And first thing he does is he removes all the common words, like articles and prepositions. He doesn't take them. He takes the essentially rare words, and he keeps a k-gram on the rare words. Okay, so of course the dimension of his vector is almost the number of words in the dictionary, but roughly it's this. But he keeps this. He the dimension is much larger because the elements now are the words. Okay, but it's key information that he keeps. Okay. Now, so this is going to be our U stat vector, U stat sub k of W. Okay, so now, if you think of the questions I put at the beginning, I have various various sources with words. Could I use this statistics, for example, to give you a proper answer on for the edit distance? The answer is no. Okay, and we'll see that. Okay, these statistics are not enough. Okay, but you can do smarter statistics. Okay, so what is a smarter statistics? Statistics now. Okay, so this vector is a bit too long. Okay, so let's imagine I take a prefix. So the prefix of size, say 5, 0, 0, 1, 0, 1. Okay. So now, if you do, so the current statistics essentially takes a random position and looks at what you see, and this is a distribution. Okay. Now, let's suppose you take 2 random positions. Okay? And now you keep, so you're going to, in a long word, you take this guy, this guy. So if you take 2, one is before the other. And now the unit is going to be the pair UV, knowing that V follows U. Okay? And this time I will call this U stat square, because I will have now a vector of pairs of UVs. Okay, so the dimension will be, if k is 2, the dimension will be 4 by 4, 16. Okay? Now, to make sure you understand, let's compute U stat, so square. But to make my life easier, I put 1 here. So in other words, if I put 1 here, I just look at 1 letter. Okay? So the U stat 1 square vector of W, and now it will be of dimension 4. Okay? So first of all, the U stat 1, if you want U stat 1, 1, I hope everybody see that you use that 1 vector of this guy is essentially 2, 3, 1, 5. Okay, I have 2, 1 and no, I should 3, 2. I have 3 zeros and 2, 1. Okay, this is a U stat 1. Okay, now what is a U stat square? So now here I'm going to count the 0 followed by a 0. Here I'm going to count 0 followed by a 1, and so on and so forth. So let's do it. Because here we can do it by hand. After that, it will be too late. So first of all, it could be, if my first guy is here, if U is here, V could also be here, because U and V, V is after U, but it could also coincide with U. Okay, so if U is here, how many possibilities I have for 0, zeros? I have this, so this one, 3. If U is here, I have 2, 3, 5, plus 1, 6. Okay, now I'm counting 0, 1. So U is here, V is here, 1, 2. U is here, 3, 4, 5. Now, 1, 0. U is here, has to be 1. 0, 1. And I guess that's the only one. And 1, 1. 1, 1 here, 1, 2, and 3. 11, 12, 15. Is 15 correct? Who do you think? Who thinks 15 is correct? What should be this number here? It should be the number of pairs that I have, so which is 2 choose 5, plus the number of possibilities that they are coincide, which is 1 choose 5. So 2 choose 5 is 5 is 10, and 1 choose 5 is 5, so it's 15. That's correct. Okay? You get the idea? But now, of course, once you understand the square, why not do the cube? You take 3 random positions and you keep them the way you see it, knowing that U is before V, which is before W. You see that? Now, if you have these statistics, you're in business for some values of P. So here would be a general P. And what I want to show you at the end is that you can solve Twitter problems with some P's, which is small. Okay? So just to give you a real motivation for this. So right now we just do U-stat simple power, but with some K. Okay? B-stat is an auxiliary statistics that will be useful for technical reason, but the real statistic is this one, of course. You know, I don't care about the blocks. I don't want to hear about the blocks, but the blocks are useful to think about it. Okay? All right. Okay. So first of all, let's do a little bit of basic stuff. So you're given a huge word, W. Question: how long does it take you to compute this, to have the U-stat vector? Well, the way it's defined, you have to read and then every word you see, you make +1 in the right position, and you advance. So you have to read the whole thing, right? So what's the point? Okay. Sorry?
And complexity.
Yes, but right now I'm thinking of P equal 1. Okay? P is 1. When you don't have parameters, think P equal 1, K is obvious, here is K is 2. I'm just make it simple. To compute exactly the U-stat vector, you need to read the data. Okay? So now what about this following thing? Forget reading the data. I take samples. Take n samples, and I do exactly the same thing on the samples. Okay? Should I get a very different vector, or should I get approximately the same vector? Okay? Think of a word of size 1 billion. Okay? You take 1,000 samples. So you have a U-stat, the correct U-stat is something like this. And then you want to compare it with some random variable, which is this. Of course, if you repeat the experiment, you get a different one, right? But then you want to compare 2 vectors. So how do we compare 2 vectors? Very important, we use the L1 norm. Okay, so I suppose you all know what the L1 norm is between 2 vectors. You make the sum of the absolute values of the differences, coefficient by coefficient. Okay? It's clear? When you take the L2 norm, you make the sum of the square of the differences, but here I take the sum of the absolute values of the differences. Okay? And I want to maintain this smaller than epsilon. You have to think of, I do everything up to epsilon. Okay, epsilon, you have to think like a physicist. Okay, you know, here the precision is epsilon, so why do you need a high precision? You can see that if you're in a real case where you're going to divide, here you know, all these numbers are going to be divided by 1 billion. So you have decimal values here, right? How many decimals do you need to carry? You know, well, you know, you don't care so much after so many decimals you want to avoid, which has exactly the same effect. Okay, so think about if I have two vectors. Okay, so in this case, my main question is this L1 distance smaller than epsilon or not? Okay, but in a similar basic operation, what you want to figure out is that you can approximate okay, so you want the U stat that you're going to get, say, minus the U stat, the real U stat, and you want to make sure that this is smaller than epsilon, but with high probabilities. All right, so now comes the fact that because I sample, I have a certain probability, of course, to be totally off. But if this probability is 10 to the minus 10, I don't care. Okay? And this is what's going to happen. Okay, so the first thing is to approximate, so to approximate this vector and to show that this is good enough. Okay, now on this slide, before we go into this approximation, okay, it's important to understand this because one key observation here important is that if you want to compute the distances exactly between two words, okay, remember edit distance. So edit distance to compute, it's a very classical problem. You can solve it by dynamic programming, and it has a complexity between n squared and n cubed depending how you do it. But something which has been studied is that it's very hard to approximate. In other words, if you want the approximate distance, you know, it doesn't really help to approximate. I mean, to approximate is as hard to compute. Okay? Whereas if you take the edit distance with moves, okay, if you want the exact value, it's an NP complete problem. Okay? But it's very simple to approximate, as we're going to see it. Okay, so here you have a typical case where you have a poly problem, which is hard because it's impossible to approximate. And then you have an NP complete problem, which is easy because it's very easy to approximate. Okay, so you turn things around. Okay, so it's very important. All right. And so for example, in this theorem here, what we're saying is that this is a relativized edit distance with moves. Okay, and then it's very simple. You just look at the L1 norm between the two U-stat vectors. Okay? And that's what we're going to see in a minute. Okay? All right. Now, how do I approximate the U-stat now? Okay, so I do something which is the basics of statistics, which is use a Chernoff bound, because I'm going to see this experiment of looking at U's. They are independent. Okay? So imagine that every time you get some U's, you generate this random variable with a 1 on the corresponding subword you see and 0 on the others. Okay? Then, when you compute the U-stat hat, the random variables, what you're actually computing is this. Right? Now, this is a sum of independent random variables. Therefore, it'll get very close to the mean. Okay? Now, what is the mean? So think of this coefficient, for example. What is, so if you want to think of this coefficient, you have to imagine that u stat hat of W, and you're looking at the second component, which corresponds to 0, 1. Okay? Now, this is a random variable. What is the expectation? Okay? You have a random variable. What is its expectation?
For this case,
exactly. But so it is always the u stat W of 0, 1. In this case, 1/3. Okay, I don't know if you see that. You take random subwords, you sum them up. Approximately, they should give you this value with a variance, but the variance is going to be very, very small, and that's what you get using a Chernoff bound. In other words, what you bound is the error on each component. Okay, so the Chernoff bound is going to give you the fact that the probability that this variable so the probability that u stat hat of W on a certain component u, say, minus u stat, so minus its mean, so the probability that this is small, and maybe epsilon divided by actually the size here, because after that I'm going to make a sum of errors. So the size is 2 to the k on a binary alphabet. You look at Chernoff bound on Wikipedia, and if you know how to look, you will find that this should be bigger than well, usually it's phrased that the probability that it's bigger than this, it's phrased, okay. The probability that deviate more is smaller than e to the usually they put a coefficient here, which is the error. So let's say epsilon over 2 to the k square. Usually they put a minus 2 divided by the number of samples. Okay, or something you can certainly, okay, so this uses, okay, so the basic is the Chernoff bound, but here we're using the fact that the random variables are bounded, 0, 1, therefore you can get a better bound, which is called a Hufting bound. And here we're using a version where we're looking at absolute error. Sometimes you're looking at what is the probability that the random variable deviate from its mean by not an absolute value, but a relative value to the mean. So with the epsilon 2 to the k multiplied by this. Okay, but so here it's an absolute difference, and of course the absolute difference is easier to treat than the relative difference. Okay, so it goes exponentially fast to 0 as n grows. Okay, so if you want to work with high probability, so remember, so this is the probability of error essentially. Okay. Remember in the property testing thing, we want to do everything with high probability. Now this is exponentially small. Okay, this as soon as n is bigger than some function of epsilon, okay, say make.
If n tends to infinity, then the power tends to 0 and the exponent tends to 1.
For me,
if you divide power, n tends to infinity, yes?
when n goes to infinity, e goes to 1 or to 0?
To 1. e to the 0 power, to the power which tends to 0.
No, but then you're talking about e to the minus.
N should be the numerator.
Yeah, thank you. Thank you. Obviously, you want this to go to 0, right? E to the, yeah, so n should be a numerator. Thank you. All right, so this should go to 0 exponentially fast, right? Of course, the other one would be slightly more difficult. So now if you turn, so at some point you will think what is the error with high probability? Then high probability means that 1 minus this coefficient, okay? That goes to 0. All right, so now, first thing using this bound, you can see that this vector, which I call ustat hat in my notation because I can really see that it's a random variable. Here it's called y sub w, okay? Now first thing is when n is of the order of, think of n as 1 over epsilon squared, okay? That's what you're going to get, maybe with a dependency on k also, but you know, k is going to be 1 over epsilon, think of this. Then this is going to be true, and therefore this will be epsilon close to that, all right? And now remember that okay, so essentially the tester, what's going to be the tester with equality? Assuming this theorem, okay, let's assume this, because otherwise we need to prove this, right? Let's assume this. So if I approximate this by my y, I approximate this factor by y sub w prime, okay? If I make sure that the approximation between this and this is smaller than, say, epsilon over 2, this one epsilon over 2, then I will make sure that the global error is less than epsilon. So my test will essentially be the following. I sample, I get y of w prime, I make the L1 norm between the two, and I look if it's bigger than epsilon or not. If it's bigger, if it's smaller than epsilon, I accept. If it's bigger than epsilon, I reject. Remember, we're doing equality. W prime. Okay? So I sample, I assume W and W prime have the same length. Okay? Otherwise, they can't be equal. I sample same positions. Okay? If I sample the same position and they are equal, the y is going to be equal to the, this guy is going to be equal to this guy. So the error will be 0. So it will be less than epsilon. Okay? Now, if they are not equal, okay, and if they are a distance bigger than epsilon, because this approximates the distance, if the distance is bigger than epsilon, that this is big, and because the error between the y is small, then the test is correct when this is bigger than epsilon, with high probabilities. Okay? So now I need, the fundamental operation is to understand why from the edit with move points of view, essentially, instead of looking at distance at words, I can just look at their Ustat vectors. Okay? Which is, of course, a key simplifications. Now you can immediately see that this is not going to, should not work for the edit distance. okay, because it's extremely easy to see words that have the same statistics, but they are far for the edit distance. So it's exactly the example I had before, where you have A's and then you have B's. Imagine you sample, you see the same statistics, and yet they are far for the edit distance. So obviously, if you want to do, you want to work with edit distance, this vector ustat is not going to be enough. Okay, but now think of the example, okay, zeros followed by 1. If you take the ustat square, okay, then it's going to work. Because with high probabilities, you'll see the zeros followed by the 1, and on the other case, you'll see the 1 followed by the zeros, and they'll be different. Okay? So that explains why, if you want to generalize this to edit distance, you have to use powers on the ustat. Okay? So let's now stick to proving this. And this is, of course, the non-trivial operation. So let's get into details. So essentially, we have two things to show that strings that are close have close statistics, and if the strings that are far have far statistics. Okay, so in other words, you want to show that if you're close, you have close statistics. If the statistics are close, the words are close. Okay. Another way is to say is the contrapositive. If you are far, the statistics are far. Okay? All right. Now to show this, I will need a B stat. So now I'm going to, one of the properties is very simple. So the property that is very simple is to show that epsilon closed strings have closed statistics. Okay? So why is it simple? So I think it's done, okay, here. Okay, so imagine that you apply a number of operation which is less than epsilon square n. So now there's still a game on an epsilon here. Okay, and I want to show that the statistic will be close. Okay, well, I compare, what do? I look at the effect of each operation. Okay, how much does the statistic change when I make an edit? How much does it change when I make a move? Okay, and so on. And for each edit operation, I look at the variations. Okay, so for example, for a simple edit, the variation is smaller than that, which is smaller than that. Okay, which is easy. But the big thing is when you make a move. Okay, so you make a move. Imagine you divide the block you're going to move it here. All right, now what's the difference on your ustat? Well, then you figure out that now you have borders on which you make mistakes. You know, if you pick a word right at the border here, you don't see it there. So potentially, but how many words are the border? You know, finitely many. Okay, you have essentially 4 borders you have changed here. So you can imagine that you figure out, and this is going to be bounded. And now if you do this operation, then you end up bounding the ustat statistics. Okay, you have to look at the variation, but I think it's very intuitive. You know, each edit operation has a small impact on the statistic vector. Okay, however, now the difficulty is doing the opposite. Okay, so you want to show the robustness of ustat. Okay, and for that, you're going to use the simple thing that the B stat is robust. Okay, so let's think about this first. Why is a B stat robust? So remember, B stat is exactly the same thing, but we're looking at blocks. Okay, now, so what happens, for example, if you have the same statistics vector? Okay, so if you have the same statistics vectors, it means that you have the same blocks, but potentially in a different order. Okay? Now, how long does it take you to reorder? Okay? Well, it takes you less than epsilon n operation. Okay, because why is that? You have to think of k is 1 over epsilon. Okay? So, so how many blocks I have? N over k, right? And I need to move. I put the first one in position, then the second one in position, and so on and so forth. So I think I'll need at most n over k move. But n over k move is epsilon n because k is 1 over epsilon. Okay? All right. So now let's suppose the two B stat are different. All right? So, for example, this. Okay, that's clearly different. Okay, so what do I do? Well, I'm going to do some, equilibrium finding. So I look at the biggest difference. Where do they differ the most? They differ the most. Okay, so here I have a 4 and a 3, and here I have a 1 and a 2. Okay, so obviously what I'm going to do is take one block which is a 1, 0, and transform it into a 0, 0. Okay, so I'm going to edit the block corresponding and equilibrate. Okay, and you can see that I will not make such many operations. Okay, and therefore the statistic will not change so much. Okay, so here is the computation. So and the result is that essentially this distance is smaller than that. So if that is small, I think the n here comes from the fact that you're looking at the absolute value. So this n here should be here for the relative distance. Okay, so so the robustness means if the statistics are close, so you have to think of if this is small, then the distance is small. Okay? And of course, that's a reason why we look at the B-stat. Okay, because clearly on the B-stat statistics, it's easier to show that closed statistics implies closed words. Okay? And now the key thing is to understand how we're going to use this to lift it so that closed statistics on the U-stat will mean closed words. Okay? Which is a non-trivial thing. Okay? The non-trivial thing is closed statistics means closed words. And it's entirely non-trivial. Okay. So for that, we need a third distribution, a third statistics, which we call block uniform, BU stat. Okay, so we're trying to do something in between now. Just imagine we're trying to do statistics that are, so block statistics, clear, U statistics, uniform statistics is very simple. Now, what should be block uniform statistics? Okay, so imagine I take big blocks here and think of big K as K squared. Okay, so okay, all right. So I have big blocks, say constant times K squared, and then what do? I take the first small block, okay, and I make a random shift by a value which is smaller than K. The T here, this T is going to be random, and is it clear that, okay, but anyway, think of, you have a first block here of size K, right? You want to essentially shift the first block randomly, okay, by taking a prefix between 0 and K. So you're removing a bit here, and to catch one block, you're removing k minus t there, right? So if k is 10, so for example, take a random t between 0 and 10, so 6. So I remove 6 here and 4 there, so that I removed one block, one small block. Okay, and I keep doing this so that eventually I end up with a slightly shorter words. Okay, because I removed, how many blocks did I remove? Well, as many as the number of big blocks, which is n over big K. Okay, but for what I do, this is small. Okay, and then now you can see that now what am I going to do? I'm looking at now the B stat of this shifted words. Okay, the shifted words I call V1. Okay, so it's shifted randomly, and because it's shifted randomly, it looks like some U stat. Okay, because what is a U stat? It is actually a B stat which is randomly shifted. Okay, so if you think of a random position, you could always say, well, a random position uniformly is a random block plus a random shift in the block. That's actually a fair thing. It's exactly what you're doing here, except you're doing a random shift on a big block that you consider as big blocks. All right. So obviously now the BU stat will be the expected B stat of this whole operation. So the BU stat is the expected value of the BU stat, which is a random operation. Okay, so here you start, you know, and you need this, right? Because otherwise it's going to be tough. All right, so 3 statistics: the block, the uniform statistics, and the statistics in between, we shifted a big block. All right, and now I want to essentially show that the U stat and the BU stat are very close. Okay, somehow, and then I will show that the B stat and the BU stat are very close. So that will give me that the B stat and the U stat are very close. That's the idea. Okay. Now, if you want to look at this, now here BU stat is some kind of a uniform distribution because it includes all the blocks of the U stat, but not as many. Yeah. You know, if you have a block of a BU stat, it is a block in U stat, but some block in U stat are missing here. So it's like having 2 uniform distributions where you have a smaller support here. Okay, so imagine you have this distribution, which is a smaller support than these other distributions. Okay, now what is the error? In other words, what is the size of this plus that, which is the L1 distance? Okay, so I want to bound. So if you have 2 distributions, mu A and mu B, then the L1 distance is exactly this. Now it's almost a geometry operation. Okay, so it's twice the difference between B minus A divided by B. Well, in our case, B minus A is going to be very small, and therefore this will be small. Okay, so now I have to estimate how many blocks I'm missing. So I have to, you know, the number of blocks that are missing, which corresponds to B minus A. Well, I compute it like this, and I compute actually K is could be actually bigger than what I said before, but if I take so I mean here you don't want, you know, that should not depend on n, but the reason why there is an n here is why is there an n here? Yes, well, because you think of so you want to think of a big block. A big block should be, of course, much bigger than K. And if k is 1 over epsilon, I have an ugly function, but it should not depend on n here. Okay? Well, believe me, you have to evaluate the small differences. Here, once you replace these values here, you end up by this function. And I don't think you should see an n here. That's my conclusion. You should never see an n here. Okay? No way, no way. This shouldn't be an n here. Okay. Now, after that, then we're getting closer to the end. So I'm really sorry for, technical details. So that explains why I'm using slides here, because if I were going to do this on a blackboard, it would be very boring. But now I want to, essentially, previous slides says that B U-stat is very close to U-stat. Okay? So now I want a proposition saying B U-stat is very close to B-stat. Okay? And in which sense? Now it's different. It said for every W, there exists a V, which is close. Okay? They're close, such that I have this. So the difference between the BU stat of W and the B stat of V is small. Alright, okay? Now, I don't think you want to, this uses a probabilistic argument. I don't know, so the end story is that I will show that the probability that the V exists is only positive. I don't know the V. Okay? Let me skip this argument because it will be, if you want to see the details, then we'll go back to it tomorrow, but you can check it for yourself. And now, here is how you combine all the pieces. Now, you assume that the distance is large, and you want to conclude that the U-stat will be large. Okay, so first of all, you start with the fact that if the B-stat, the fact that the B-stat is bigger than the distance, okay, then you use the fact that you approximate the B-stat of this guy by some BU-stat. Okay, so of another word, so you use the previous lemma. And then you use the lemma before where you compare the BU-stat with the U-stat. And then you put the errors together, and eventually you show that this is true. Okay, so this is, hidden in this property testing are a whole bunch of arguments like this. I show you the details for one of the arguments. If you really want to understand, you have to dig into these proofs. But now I just want to give you the global picture. So the global picture is, so it's written here. Okay, so why do I have a tester for equality? If the words are equal, then I accept with probability 1. If the words are epsilon squared, if they are epsilon far, I reject with probability 2/3, which is high enough. And then this is an extra statement I get. I get some extra thing. What happened if they are very, very close? If they're very, very close, it just happened that I'm still correct. I mean, you prefer when you're very, very close to accept than to reject. And here I can actually quantify this, but this condition in the middle, I don't need it. This is some extra gain I get for free. Okay, most important is this and that. Okay, so the end situation is that we can replace essentially a word by a statistical information from the edit distance with move points of view. Okay, we edit, we can't. All right, so now tomorrow we will now attack the main problem, which is a regular expression. Okay, then we can do a lot of other stuff. For example, we can compare languages and so on and so forth. Okay, but maybe I won't go into much into this. And so now what happens with regular expressions. Okay, so remember, so let me give you a sketch and then we'll do the argument tomorrow. So let's look at the picture. Let's look at the picture. Okay, here is an example. Let's look at the example. Okay, the regular expression is this. Okay, 0, 1, 0 star, 0 star, 1 star, plus 0, 1 star, 1, 0 star, 1 star. Okay, so let's assume epsilon is 0.5, therefore k is 2. Okay, so I'm doing 50% of error here. So 50% of error is not so good, but of course if you understand, you can make epsilon the epsilon you want. Okay, the algorithm works for any epsilon. Okay, all right. So now think of each. Okay, think of first this component. Okay, and then that component. Okay, we have two distinct components. And obviously, what you want to think about is the set of U stat W, so for some k, when W is in R. Okay? That's what you have to think about. So let's split R into two pieces, R1, R2. Okay, let's think of R1. So see, R1 has three basic loops, okay, that you can repeat. This guy, and this guy. All right? So now let's define a U-stat vector for a loop as follows. So what should be, so this is a definition. What should be U-stat k of some loop, for example, 0, 1, 0 star. Okay? Well, my definition is it's going to be the limit of U stat k when n goes to infinity of U stat k of 0, 1, 0 to the n. Okay? So imagine that you have 0, 1, 0, 0, 1, 0, and it goes to infinity. Which vector will you go to? Okay? So now, I don't know if you see, but of course it's very easy to see for 0 star. If you say 0 stars, which vector do I go to? Okay, k equals 2. You should go to this vector for 0 star. Okay? You have a density of 1 on zeros, and the rest is 0. If you have 1 star, you should go to this vector. You have a density of 1. All right. So why is it 1/3, 1/3, 1/3 for 0, 1, 0, 0, 1, 0? Well, just write 0, 1, 0, 0, 1, 0, 0, 1, 0, and observe that you have actually exactly the same probability to find a 1, 0, then a 0, 0, and a 0, 1. Okay? Like exactly the same number. Okay? So, and the number is 1/3, 1/3, 1/3. Okay? So now, build the polytop with summit this U-stat vector, this U-stat vector, this U-stat vector. And it just happens that all the points that are correct for this regular expression have a U-stat that find itself here in the complex of the 3 points. Why is that? Because it means that you have a certain proportion here, plus a proportion there, plus a proportion there. Okay? But the sum of the proportion has to be n. So you can write the word for this regular expression as, say, 0, 1, 0 to some alpha 1, 0 to some alpha 2, and then 1 to some alpha 3, where you have alpha 1 plus alpha 2 plus alpha 3 equals 1. Okay? So for example, if alpha 1 is 1/3, alpha 2 is 1/3, alpha 3 is 1/3, then you will be exactly in the middle. Okay? Now, think of a word where you have half of these guys are 1, 0, 0, 1, 0, and half of these guys have zeros, and you don't have ones. Then you are precisely in between here. You should be here. Okay? And you can do the same thing for the other components. So you can see that the U-stat vector of a regular expression, so that's what we will show tomorrow, is a union of polytopes that are very simple to define. And now the membership tester is going to be the following. We'll see that tomorrow. Take your word, sample it, get this U-stat hat, here it's called YW, plot it somewhere here, and look at the distance to the polytope. If the distance is bigger than epsilon, reject. If it's smaller than epsilon, accept. And that's it. Okay? So the property testing, once you have the right statistics, is made of very simple algorithms. Okay? As usually the most natural one you can think of. Okay? Here, to compute this distance, you still have to use a linear program, because the distance to a polytope for L1 distance, you have to use the linear program. So you have to get the polytope, you have to get linear program, you use linear programming, and you estimate the distance. But the dimension here of this structure is totally finite. Okay? It has nothing to do with n. Okay? The dimension is here, depends on the size of the alphabet, and depends on k, but n is gone. Okay? N is gone, so therefore the number of queries is finite. Usually 1 over epsilon square. Okay? So we'll go back tomorrow on this, and then after that we try to generalize this approach to the edit distance. Because edit distance with moves, you know, some people don't like the moves. Okay. One thing is, which is important and is part of the motivation, if you, for example, work on DNA sequences and biological data, but for example DNA sequences, well, in the DNA sequences in biology, they exist in three-dimensional space, right? And they curve and they make a whole bunch of features, and sometimes they split, right? And they reassemble somewhere else. Okay? Well, if you think of what a DNA split is, so what they call DNA split in biology is this operation. So you have to think of your sequence like this. Okay, and then if you have a geometrical situation like this, then some binding may occur here, and if some binding occurs, then you know the thing splits like that, and this bit could go to another DNA, or maybe there. If it goes there, it's exactly a move. Okay, but it may go to actually another bits. Okay. So a move is something which is very natural in many areas of biological data. Okay, but we'll see that if we have the edit distance with move, then a lot of things get very simple. And if you really want the edit distance, you should get higher statistics up to some level that we'll quantify tomorrow. And this will lead to real applications. Okay, if you have these big sources of tweets, I'm going to show you how to do a whole bunch of things, using the U-stat to some power. Now the power usually is going to be 3 or 4. Okay, not much higher than that. Okay, so that's so tomorrow. When do we meet? Because we don't meet at the normal time.
It's up to you. We can start at 12, at 1 p.m., at 2 p.m.
What do you prefer? Let's do some crowdsourcing.
I prefer.
What do you prefer?
I prefer,
Okay, so 12? 12 or 11?
Let's vote for 11.
Who goes for 11? Okay, who goes for 12? Okay, let's go 12. Sorry. That's a majority voting.